Thank you, Valerio. Thank you, Michael, and thank you everyone for organizing this workshop and these, this exciting session on the mathematics of planet Earth in general and on stochastic methods. So Michael concluded his talk by saying that we are here not only to think about the climate, but also to understand the mathematical properties of climate dynamics and have fun. So I propose playing a little bit with ice ages. And before I start, we were given this paper to read 2 days ago, which I did. I did my homework. And it starts with the climate system is a forced, dissipative, nonlinear, it was written complex as well, heterogeneous system that is out of thermodynamic equilibrium. And I think it was the perfect starting for a paper on the physics of climate variability. So it means we take here the point of view of physicists. That means that we are looking after basically dynamics. We will write differential equations. Time is an important factor, important element. And we look at mechanisms, forcings, feedbacks. And we will basically toying with a little bit of mathematics. And I tend to do it as a physicist after it's my training, which means that sometimes it's done a little bit by hand. We do things that mathematicians regard a little bit suspiciously, and then we give mathematicians the messy stuff for cleaning up. And this is also what I will do during this talk. So we are really after gaining intuition here. This said, sometimes we write models which lose a little bit the initial physical motivation. And Lorenz's model, which I would prefer to call Salzman's-Lorentz model 1963, is a good example of it. I mean, if you take this dynamical system written by Lorentz, by Salzman and Lorentz, it was originally used to study convection. And the parameters that Lorentz used in his 1963 paper are not, in fact, compatible with the original physical hypothesis, and yet it provided a lot of insight. And so you will see that when we do that with ice ages, with the glacial-interglacial cycles, we are sometimes in the same situation. So sometimes the models we propose are no longer quite physically right, but they remain mathematically insightful. And that's the kind of gaming we will do now for the next 45 minutes. So first, I would like to give you a little bit of context. So this figure was published in a highly cited journal, the Proceedings of the National Academy of Science last year. There is a lot to say about it, but it's nice to give some context. So what do you see? It's a time series. It's obviously a pseudo time series. Some call it a splice. So basically you put time slices next to each other to give you a picture of climate evolution. And the time axis, be careful, it's broken. Here we speak of million years. Here we speak of thousands of years. Here we speak of decades or maybe centuries. So the y-axis is delta T. We don't know what was the past temperature, to be honest. There is not such a thing as a proxy for globally average temperature. And to be clear, many of these data are usually hemispherically biased, so they reflect more what's happening in one hemisphere rather than the other. And it's not always the same hemisphere which dominates the result here. So we have to be a little bit careful. But nevertheless, it gives you a reasonably good idea of a few elements. One is that most of the time, especially over what we call the Cenozoic, the temperature was larger than today. We are going back to that. In fact, that was the purpose of that paper, and maybe a little bit too quickly for safety, but that's basically the point. And what we will be looking at during this presentation are these glacial-interglacial cycles, which started, roughly speaking, 3 million years ago, and which were biggest over the last million years. So it's an oscillation between, or at least, yes, let's call it an oscillation, between interglacials, and during an interglacial, the climate is more or less the same as today, more or less, and glacial maxima. And so the last glacial maximum, the latest, or maybe the last, was 20,000 years ago. So you have to imagine the global average temperature was of the order of 4 or 5 degrees, smaller than today, but here in France, it was probably more like 7, 8, or maybe 10 degrees, less than today. And you had big ice sheets. One was located over Northern America, one was located over Fennoscandia, and together these ice sheets represented 40 million cubic kilometers of ice. So that is a 120 meters of sea level change compared to today, because of obviously all this water which was on the ice had to be taken from the ocean, and so you have a sea level drop. So basically, people have been aware that there was such a thing as an ice age for some time, and it's mainly in the 19th century that evidence started to accumulate and people started to have an idea of where the ice sheets were, what was their volume, etc. And it's also in the early 20th century that they started to understand that it was a recursive event, or at least that you had several ice ages before. But you have to wait until the 50s, and especially when you have this big effort to drill deep sea core in the ocean, then paleoceanographers started to have a very clear idea of the sequence of past ice ages. And now we have these sequences which are 60 million years long. So bear that in mind. It means that we have a clear idea of what ice ages are. Well, the cyclicity of ice age is something we have a clear idea about we have had a clear idea about for 50 years. We will sometimes speak during this presentation about the changes in CO2 concentration. And that is something we only know about we have known about for 20 years, more or less. So that's, after all, we will take a lot of things for granted, but it's still reasonably new phenomenology, if you like. So just one of those curves. So this represents 1 million years of history. Well, sorry, 800,000 years. Forget about the future. Obviously, people want to know about the future, but we will concentrate on the past. So you have two time series here, which are famously, frequently shown to various audiences interested in ice ages. So one, it's a bit cryptic. It's written delta at 18O. So what it means, when you drill the deep ocean, you find sediments, and many of these sediments are made of small organisms. They are called foraminifera, which have a shell of calcite. And calcite, if you know a bit of chemistry, it's CaCO3. And if you look at the oxygen isotopic ratio between 16 and 18, you have and I'm making shortcuts here because you want to do math and not chemistry, but you have an idea of the level of glaciation of the Earth, if you like. So this means a glacial maximum. This means an interglacial. And this is a CO2 concentration that you recover by drilling ice in Antarctica. That's the only safe place where you can get CO2 from, because you need a very, very deep freeze air to recover reliably CO2. Okay, let's move on. What you see is that it's not such a harmonic cycle. I mean, it's not just a sine wave. First, it looks like it evolves over time, because here it's like more a hectic back and through, and here it really takes a sawtooth shape signal, which means that it takes you time to have a full glaciation, and then you have a reasonably rapid deglaciation. So it's interesting. Now we have all the records. We know about the last 3 million years with quite a lot of detail. But for a very long time, keep in mind that people have only seen the latest cycle, or maybe until 15 or 20 years ago, they only knew about the latest 4 cycles. And if you just look at the latest 4 cycles, you have really a very clear vision that you have accumulation of ice, deglaciation, accumulation of ice, deglaciation, aborted glacial inception, deglaciation, accumulation of ice, deglaciation, accumulation, etc., etc. So that somehow has imprinted also the research on ice age. As I told you, people have known that there were ice ages for some time, and one person which is frequently cited as one of the theorists of ice age is Milutin Milankovic. It's not the only one, but we'll talk about him today. So Milutin Milankovic was a Serbian. Well, he was known in what is today Croatia, which makes a lot of difficulties. But basically, he laid out a theory according to which the ice ages are caused by changes in the various parameters which characterize the Earth orbit of the Earth, the Earth orbit around the Sun. So one of these parameters is obliquity. You know, because we have obliquity, we have seasons. And we have known for some time as well, well before Milankovitch, that obliquity varies in time. Sometimes it's 22 degrees, sometimes it's 25, and there is a cycle of 40,000 years. So Milankovitch was aware of that. There is another important element which Milankovitch was aware of, is that the eccentricity of the orbit changes. So sometimes it's almost circular, as it is today, sometimes it's more elliptic, while the maximum eccentricity is 0.05, so it's never quite like a comet, but it can be more eccentric. And it matters, because depending on whether you are closest to the Earth, to the Sun, in summer or in winter, you get a bit more or a bit less insolation, incoming solar radiation, in winter and in summer. So the cycles of eccentricity, you can basically see it as a sum of harmonics around 100 and 400,000 years. And then the precession, so which decides whether you are closer to the Sun in summer or in winter, this cycle is of the order of 20,000 years. And Milutin was aware of all of that. And so he computed the changes in incoming solar radiation that you should get at the surface of the Earth. It's relatively simple geometry, it's not very difficult. But it also took into account the radiative properties of the atmosphere and also the snow albedo feedback. So he understood that if it is colder, you have more snow, and as you have more snow, you reflect more solar radiation to the space, and so you get it even colder. And so his idea was he devised a quantity which is called the latitude equivalent on the snow line. There is a lot of hypothesis behind this calculation, but it has good historical value. And so you see the scale, it's 600,000 years represented here. And he predicted those times by playing around with the orbit of the Earth. And what he considered is that the summer season is crucial. It's an old idea which is from the 19th century. So essentially, if you have less radiation in summer, the snow that you have accumulated in winter persists over the summer. You know that if you do a bit of mountaineering, I mean, you know that in June or July you still have a few, how do you call that in English, a neve? It can be a bit dangerous, so you can imagine that if you have less radiation, the neve persists over the summer, and it's how you start an ice age. Okay, so that's Milankovitch's take. So there was a bit of skepticism about Milankovitch's theory. He's not the only one to have theorized about Ice Age, even though we tend to cite him today quite a lot. So if you dig a little bit of the literature, for example, you would find this paper by Peter Whale. It's by the way, in a very nice book of the American Meteorological Society, which contained a lot of very fascinating contributions back in 1968, including by Lawrence, by the way. And so I don't ask you to read the whole abstract. It was just a kind to find a figure to summarize this. The fact that the paper exists. So don't concentrate on what is written, just listen to what I'm trying to explain. So what Peter Whale theorized is that you have ice ages as a self-sustained limit cycle. That was his idea. And his theory involved changes in the thermohaline circulation, so basically the deep ocean circulation, which would sometimes be deeper in the northern Atlantic with a lot of convection, sometimes shallower, and in fact this kind of deep circulation oscillation has since gained a bit of popularity for the theory of Heinrich events, and I will not come back to that now, and that's Garösger events. It's beyond the scope of this talk, but it's interesting that a theory about ice ages sometimes makes its way as still relevant to explain another phenomenon. Right, so I would like to come back a little bit to Milankovitch. So this is the original curve. And now I will tell you the kind of curve that we can draw today. So that green curve would be what more or less Milankovitch would have drawn as his effective latitude. It's a quantity which is called a caloric summer insolation. If you like, it's like insolation integrated over summer, which varies with, if you have good eyes, or at least you are very quick at decoding diagrams, looking at the time here, there is a main cyclicity of the order of 40,000 years. But given that you mess up with obliquity and precession, this phenomenon being closer to the Earth in summer and winter, you have a kind of sum of periods which are not a ratio of each other. So you create a quasi-periodic signal. We do a bit of math here. So now you look at the curve of ice ages. Those I already showed a little bit earlier. And it's hard to say that this matches that one. It's not quite the same thing. So that's one of the reasons there was a bit of controversy about Milankovitch, and it's also what made people think more. And those people in the, like Nick Shackleton, Wally Brooker, were very active in the 70s. They noticed that, in fact, if you pay attention to all these secondary oscillations, it matches the curve pretty well. I don't show that here, but trust them, and it's right. But what the curve does not predict is these big jumps, so the deglaciations. Indeed, we have transitioned from the last glacial maximum to the Holocene, the current period, in 10,000 years. So all of that happens in the 60s and early 70s. And who here is aware of and knows about René Thom, just as a kind of a few people, but not everyone, René Thom. So René Thom was, I'm not best placed to speak about him. I'm sure those people who told they know him know better, but he was a famous French mathematician, and he got the Fields Medal, so he's more than an amateur. And one of his latest contributions was about catastrophe theory, and it became a bit. I mean, so the idea was to he used the topology, the reasoning about the topology of surfaces and mixing dynamical system reasoning with the topology with geometrical reasoning to classify catastrophes. So basically, like typically we would talk today about the stock market crash or maybe the end of an ice age. And the geologist Dave McHale, who is still around, had this idea that maybe we can recycle this idea of René Thom to refer to the deglaciation. And he made this pretty complicated diagram, which is directly inspired from René Thom's book. And it's hard to explain exactly what it shows. And I will show you an easier diagram in a minute, but the whole idea is that because you change incoming solar radiation, you increase ice volume. And there is a tendency to increase ice volume, which means that you have lower insolation, you gain ice. You have more insolation, you lose a bit, and then you gain again, you lose a bit, and it's how you build a glacial maximum. And at some point, you have a catastrophe which happens, and all the ice is melting. So McHale is a glaciologist, so he was aware of the works of glaciologists at his time. And for example, there is among them one who was very active. There were a few famous names like Birchfield, Urleman, so he's still around, but the one maybe he was referring to was Weirtman, I cannot pronounce his name correctly, who already in the early 60s realized that a big ice sheet can become unstable. And so you have this glaciological argument that when you have grown big ice sheets, because of the isostatic depression, and also because the way the ice sheet could start to melt, then it can start a deglaciation and accelerate the deglaciation. It's a glaciological argument. And again, we have not much time to go into the detailed physics of it, but it's still considered to be something which is reasonably plausible, even though the exact details of the mechanism put forward by Weirtman would not be taken as quite true today. So this is inspired from math and put together by a glaciologist. I can show you a similar diagram by Didier Paillard, who used to be, was he one of your students, wasn't he, Michael?
He spent a year when he wrote the paper together, but eventually he did his PhD.
Okay. So this is what Didier Paillard published in Nature in 1998. It's a diagram which basically, I think, makes it simpler, the idea of McHale, but the idea is the same. So what do you see? His point is that the Earth, or the glacial system, if you like, the climate, has various states, like interglacial, semi-glacial, and full glacial. And when you are in one of those states, you are influenced by the insolations. You can gain ice or lose ice depending on the forcing. And as you cross various thresholds, you can transition from interglacial to glacial, and I agree that the diagram is not that easy to read, in fact. And when you're in a glacial, you can transition because of the forcing to a full glacial. And when you're in a full glacial, you are considered to be in a vulnerable position, which means that at that point, an increase in insolation will send you back to an interglacial. So it's basically the sketchy way to materialize this idea. And in fact, if you take this model, it has a few free parameters, to be honest. You tune it a little bit. And this is still a copy-paste from his paper. You can reproduce what was at that time, in 1998, one of the reference curves for Ice Age. And this is a copy-paste of the paper, and Didier Paillard used here a convention used by geologists. It's to write time going from the right to the left. It makes our life a little bit complicated for us, but we understand the rationale of this convention, because obviously when geologists recover a record, they want to put the signal as a function of depth, and that means age. And so when you start your PhD in paleoclimate, you are told by your supervisor that you should learn to read time from the right to the left. Anyway, if you look at this curve, which is the model output, and if you look at this curve, which was at that time the reference, you say, oh, well, we got the idea. We got the idea. And Didier went on further, and he represented the evolution of the Ice Age for 3 million years. And I did not insist about so far, but in fact, if you look over the last 2 or 3 million years, you have a change in the regime of ice ages, and he captured that as well. I will not insist too much on that at the moment, because I want to go to advance. Okay, we are at that point in 1998, so that means almost 20 years ago. And you could say at that point that you have the mathematical idea right, which means you accumulate ice, and at some point you deglaciate everything. And so you have to pass on to these people who do very detailed physics to see whether the mechanism of deglaciation is correct, whether you can actually have a catastrophe, how you model an ice stream, and you could say the story is done. And to some extent it was, and yet I will show that you can push it much, much further. Before I'm doing this, I need to do a little bit excursion back to the early 1980s. So well before this idea of Didier Paillard, but already after the Macael idea, you had a few contributions by Roberto Benzi and Catherine and Grégoire Nicolis, who are mathematicians and physicists, and were also a bit intrigued by this idea of ice ages. And they put together this idea of stochastic resonance, and I think most of you are a little bit familiar with what it means. So the argument was to say, okay, if you take the global Earth, and if you are considered that you take the perspective of Boudico cellars, and I think many of you have heard about it, and if you don't, Michael can, I'm sure, give you a full lecture on it. But it's this basic idea that you take the total amount of incoming radiation coming to the Earth, you have a certain albedo, you radiate energy back to space, and this determines the temperature. So if you start from this starting point, if you take this starting point, you say that what controls the temperature should be the globally averaged insolation. It happens that this globally averaged radiation is only a function of eccentricity. You can show that. It's easy to think about it, because obviously if you have the Earth with more or less obliquity, it should not change the total amount of radiation you get. And if you are interested in all the radiation you get over 1 year, where you start from is not important as well, so the precession effect does not matter. It's a simple symmetry argument. So what remains is eccentricity. But in fact, eccentricity changes the incoming solar radiation very little, but by a fraction of watt per meter square effectively. And so their point was, how can we explain ice ages by such small changes in incoming solar radiation? And so they took this Boudico-Cellars model, which tells you that if you have a snow albedo feedback, maybe you have 2 stable states, one which is fully glaciated and one which is ice-free. And you have a potential barrier to go from the one to the next, and you can see that from the equations. So basically, you can model climate as a potential walk between these two ice-free and ice-full states. However, if you are in a deterministic case, once you are trapped in one state, you cannot escape. So their point is that maybe eccentricity is somehow changing the relative depth of the two potentials, because if you have a bit more insolation, then these states become a bit more stable. If you have a bit less insolation, these states becomes a little bit less stable, but not to the point of forcing the transition. And then if you, to this background, you add a bit of additive noise, then the noise makes the transition actually possible, but not at any time. It makes it much more likely if you have one shallow well and one deep well. In that case, the transition from the right to the left is much more likely than the transition from the left to the right. There is a full mathematical theory about it, which involves a quantity which is called the Cramer's escape rate. All of that is relatively standard physics nowadays, and standard stochastic mathematics. The whole point is that if you respect a certain ratio between the frequency of the forcing and the escape rate, you can create a phenomenon called stochastic resonance. And this stochastic resonance will create typical trajectories, which are noisy escapes from maximum and a minimum. And this transition will not occur completely at random. There is obviously a stochastic component. But if you consider the spectrum, you will find there is a huge amplification, surprising amplification of the forcing period. The spectrum here is in blue. The yellow is an approximation to the spectrum that we worked a little bit with Peter Ditlevsen. I'm showing this and deliberately choose to burn a little bit of my time because we don't believe stochastic resonance is a valid explanation of ice ages. And yet, it turned to be mathematically very insightful, and I think if you go upstairs, you will still see a few posters of people interested in stochastic resonance. Because there is a lot of theory to do about it. You can think about the various kind of noises. You have to put additive noise. Which kind of noise? You can propose intermittency, intermittent processes, for example, as the forcing. So you can do a lot of very interesting mathematics, even though I would say the original physical motivation I think is completely outdated. And the reason why it is outdated is the following. I will skip this slide, it's about the telegraph process, but I need to rush. I started the explanation and using Milankovitch's theory to say that insolation and the insolation forcing of ice ages actually has to do with obliquity and precession. So in fact, what climate scientists consider is that the important quantity in this case is not so much a total amount of radiation you get, but how this radiation is distributed across seasons and across latitudes. And this is why we call it the Milankovitch forcing, because Milankovitch was very well aware of that. So if you consider, for example, summer solstice insolation, it's not quite the same as the caloric insolation I showed, but it's the same idea. You see, in fact, that you have this effect of precession. You have some effect of obliquity, which is more evident at other places. And what eccentricity is doing is it's to modulate the envelope of this curve. So the red curve is eccentricity. And the red curve is, if you like, the forcing. So if you do a spectrum analysis of the forcing, and in fact, my supervisor spent quite a lot of time, André Berger, spent quite a lot of time in finding a harmonic decomposition of this insolation, you get a spectrum, which I will zoom in a minute, which is this one, and which is different from the spectrum of eccentricity. That would be the power spectrum of the data, which I will not insist too much upon here at the moment. So if you zoom on the harmonics, so basically the frequency of the sines and cosines, you will find in the forcing, you have a very rich signal. So you see it as a quasi-periodic forcing with many components. And for precession, you have many components around a period of 20,000 years. For obliquity, you have a smaller number of dominant components around 40,000 years. So it means that we are looking, if we want to model climate as a dynamical system, we are looking at a dynamical system which certainly is noisy, there is no doubt about that, but also which is forced by a quasi-periodic signal. So what can we do about that? I'm still backwards to Didier Paillard and cite here a paper from the 1990s. Barry Salzman, I told you that Barry Salzman, I think to my understanding, is actually the actual author of the Lorentz model. He wrote quite a number of dynamical systems which look like, in fact, the Lorentz system, for the good reasons, because Lorentz system is Salzman's system, but also to model not only convection, but to model ice ages. It's a time that also Michael was himself very active with Hervé Le Treux in writing other dynamical systems. I cannot make a full survey here. We'll concentrate on this one, but all these works is highly significant. There was a lot of creativity and insight in those times. Maybe more than today, at least for the ice age question. I think my contribution is really incremental compared to that. So this is a dynamical system, and you have three variables: ice volume, CO2 concentration, because at that time Salzman understood that CO2 was maybe important, with a lot of nonlinearity in the CO2 equation. And this is very, very bold in the sense that we don't know, and still today we would have a very hard time in writing a dynamical system equation for CO2. We can do that for ice, and strangely Salzman just put linear terms, and maybe it's a missed opportunity maybe. And he put all the nonlinear terms in CO2. I think this is very controversial. I think I disagree with that. And then there is a third quantity, which would be the deep ocean temperature. But it doesn't matter. Let's forget about the phenomenology and concentrate on the math. I did not do a copy-paste here, but obviously what Barry Salzman did, he published in Climate Dynamics and other journals with the curve like Didier Paillard did, the curve of the output of his model, the curve of the benthic foraminifera, the delta 18O, and showing how, look, it matches very nicely. And when I started my own work 20 years ago, I tried just to reproduce these results. And I realized how tough it was to just get the same curve. In fact, and this is shown by this little graphic, you have two models here. One is the Salzman 1990, another one which I will not talk about, but I copied the path from one of my papers. It's by Elie Zipperman. But they both have the same property, is that if you change a tiny little bit the input parameters, but when I say a tiny little bit, it can be 10 digits after the comma, you have different realizations. So it looks like there is a very strong instability of the trajectories. Here you start on the same trajectory, then it goes on another one with a different timing of the glaciations, and then you come back on the same one. And this is the phenomenon I wanted to understand and explain. And to do that, you can actually toy with an even simpler model. I mean, a shamingly simple model. You take one of the simplest oscillators you can think of, and this would be the van der Pol oscillator. I take for, yeah.
I really have to say that it was Alfonso Sutera who also was one of the main authors of
for that one.
Stochastic resonance mechanism, who suggested to Barry Salzman to make his climate oscillator look like the van der Pol oscillator.
Okay.
And there's a later, I forget exactly which paper, which is Salzman Sutera or Sutera Salzman.
1984, yes.
Okay.
It's a 2D model.
Just for the completeness of history.
No, but it's nice because obviously I enter all this game later than you, and consequently I sometimes have a distorted view of history. So it's nice that you put things straight back. So in fact, yeah. So Salzman never published a van der Pol oscillator, but he was clearly inspired by it, and understand the advice of Sutera. So I mean, maybe I took it a bit more boldly even. I just took the van der Pol oscillator, and it works. And in fact, you can easily tune the van der Pol oscillator to have a curve which looks like ice ages. You just have to add a bias which makes it look like a Fitzhugh-Nagumo, in fact, oscillator, if you want. So what you have, this is a few copy-paste from earlier papers, so it's not entirely consistent. The labeling is not always consistent. Maybe the parameters not always the same. But the whole point I want to show here is that you put a bit of additive noise to these oscillators, which are forced by the astronomical forcing, and then you easily generate different trajectories, which sometimes, I mean, realign back. And I thought maybe there is something to investigate here, because you have these big projects which want to run ice age trajectories with GCMs, with general circulation models, over 2 million years. And if there is a huge sensitivity to noise, or at least if the phenomenon we describe here has some interest, then in fact it means that there is probably no chance of simulating the exact IC trajectory just from initial conditions. And I want to insist, this is not a sensitivity to initial conditions. It's a sensitivity to additive noise, or a sensitivity to parameter noise, or a sensitivity to changes in parameter. So basically, the initial conditions here are not very important. So we are in presence of systems which are either forced by the astronomical forcing or forced by the astronomical forcing plus noise. And one way to think about it is to use the pullback attractor, because they are not autonomous. So this is maybe a not very nice sketch, because I have to count on my own artistic abilities on the computer, which are not that great. But the whole point is the following. Michael already explained it. So basically, you consider the situation at a certain time. And here, this is the deterministic case. You just have the astronomical forcing, no noise. And you consider that you started the system a very long time ago from arbitrary initial conditions. But obviously, these initial conditions have to live in a certain domain. Depending on where you started the system, you will land on one or the other solution. But the point is that even though you have a choice between an infinite number of initial conditions, if you started very long time ago, then you come up on a small number of possible solutions. And that is a manifestation of what people call generalized synchronization. So the forcing is not periodic, so you cannot speak so much about phase synchronization. The forcing is aperiodic or quasi-periodic, but it can be aperiodic. But still, you see that there is a form of synchronization by the fact that over time, the mean greatest Lyapunov exponent is negative. So that's one of those things that maybe you can ask mathematicians whether there is a strict equivalence between having the smaller than zero greatest Lyapunov exponent and the fact that you have a finite number of solutions. Applied mathematicians tend to agree, though I haven't seen a proof about this. So, where it becomes interesting, I know I don't have much time, but I will try to go through it. Imagine that your forcing is periodic. So you just have a periodic forcing. In this case, you can fall on the usual theory of synchronization and speak of phase synchronization. What it means, suppose that you have a forcing of 20,000 years, and your system responds by a period, an output period of 60,000 years, 3 times. This is something that can happen. I mean, you can force an oscillator. I mean, this is the Arnold-Tong stuff. So you force an oscillator by a periodic forcing, and the output is a ratio, a number of these periods. In that case, you can convince yourself quite easily that you will have 3 possible solutions. So in other words, you will have a pullback section with 3 points. But there is another way to say exactly the same thing. If you take a picture of your system every period of the forcing, then you will create a Poincaré section. It's the right time to use this name. And you will also find 3 points on it. So basically, if there is a periodic forcing, there is an isomorphism between the pullback section and the Poincaré section, what I call the stroboscopic section. You need a bit of time to convince yourself of that, but believe me, this is true. This is solid. So now suppose that you have this periodic forcing, and you perturb this periodic forcing. On the sum of it, you put another periodic forcing. What happens? You have different possibilities. An easy one is that on your stroboscopic section on the right-hand side, because you have this extra forcing, you will start to generate small circles around the points. Because given you have this extra forcing, you don't always land exactly on the same point. And so this is the scenario which is shown here. So in this case, you have a quasi-periodic forcing, and you still see that there is a kind of synchronization of the main component, but you have created small orbits around that. However, you can convince yourself that the pullback section is still a finite number of points. So you still have generalized synchronization, and you have still a kind of phase locking, but which has become a little bit fuzzy because you have this quasi-periodic forcing. So now you can anticipate what will happen. That if you increase the amplitude of this second component, you may come to a point where the ellipses will touch each other. And here you have two scenarios. One is that you lose synchronization altogether, and so you will have a quasi-periodic response. But another possibility, so another kind of bifurcation, is the bifurcation to a strange non-chaotic attractor. And we have to be careful. Here the word attractor is used in the traditional sense. It's not a pullback attractor. So it's basically what you see on the Poincaré section. And that is not obvious from what you see here, but this is a strange geometry. So in fact, there is an infinite number of points where the distance between the attractor and the repeller is 0. But this contact zone forms actually a zero measure. So one of the works we did is to characterize different models and see those models of ice stage which produce strange non-chaotic attractors and others which produce quasi-periodic attractors and some which just produce chaos. And this is a complicated figure. It was drawn by my colleague and friend Takahito Mitsui. These are three models, Payar, Salzman and Mash 90. And this is Salzman and Nash 90, but with parameters which actually create chaos. Yeah, 5 minutes. It's what I need. And so the curve is the amplitude, in this case, the level of the amount of ice, if you want, with respect to two components of the phase of the forcing. So it's a bit complicated diagrams, but visually, you immediately see a qualitative difference between what Payar gives you, what this strange non-chaotic attractor gives you, and what this chaotic attractor gives you. And there is, in fact, a quite abundant literature about strange non-chaotic attractors which allow you to characterize what's going on. So last very complicated graphic, and then we go back to smooth stuff. This is, you know this syndrome that when you publish one of you think is your best paper in a completely obscure journal that no one reads. So this is the case of that one. I'm very proud of that paper, but it has 0 citation because it's one of the series published by the Institute of Mathematics of Rome in them, with really big respect because they do a fantastic work, but they just need the impact factor. Yet I will show you this figure. So what it shows. I know I have 2 minutes to show it, but it's fine. So you start from arbitrary initial conditions, and what happens is that depending on your initial conditions, you land after a very long time on a pullback section in a deterministic case which is made of 2 points. So it's basically a non-autonomous generalization of the concept of attractor. So if I noise it up, I could start the whole framework of random dynamical systems and random attractor. I don't do that. I just consider the pullback section and admit that depending on the stochastic realization, I will actually generate a probability distribution around these 2 points. So it's a kind of a hybrid attractor. It's semi-pullback and semi-classical, if you want. And I count the number of spots I have. And there is a lot of stuff which is very fascinating. First, the number of spots you will see is not equal to the number of pullback attractors. It's generally larger because there are what I call ghost pullback attractors which are revealed by the noise. And on the other hand, even if you are in a chaotic case, you will still find clusters, but with a lot of leakage between the clusters. And so the picture that reveals is that you have 3 cases, one with a quasi-periodic forcing, one with a strange non-chaotic attractor, and one with a chaotic attractor. The top curve in black is the number of clusters. The red curve, I'm missing time, but basically it's the spread of states. So that would be, this would be S. This would be N. And the blue is a finite type Lyapunov exponent. And so what happens is that in the deterministic case, you made a very clear-cut distinction between strange non-chaotic and chaotic. In a finite time case, which is noised up, then this distinction is much more qualitative and in fact much more blurred. So even if you have, for example, a chaotic system, over a finite time, you can generate a trajectory which, in fact, is very similar to the one which is given to you by the Payar model, and yet the mathematical properties of the model are very different. That finishes this talk. Over the last 15 years, we did more than what I showed here. This is still a view. I mean, all these papers are still centered on this idea that you're trying to learn what you can learn by modeling ice ages as a dynamical system. It's not the only way to approach ice age. It's not the only way to approach climate dynamics, and we do other stuff. And more or less for all these papers, at some time you are driven at the limit, at the boundary between what is physically realistic and what is mathematically insightful. And sometimes you are driven a little bit too far ahead. Look at the time scale here. I mean, in one of these experiments, we consider 100 million years. There's no meaning in the sense of ice ages. They lasted 1 million years. And yet we are learning about the mathematical properties. I think it's fine to do these excursions. Lorentz did it, and many other people did it before us. So I think it's allowed, but sometimes also we need to be a bit careful on the way back. That means basically implementing back the conclusions we have about the mathematical properties in your description of the physical system. That sometimes can be a bit dangerous to do. That's it. Thank you very much.
Thanks a lot, Michel. And yes, comment, Berenger, please, 1 second. I do my exercise. Please.
Yes, thanks a lot, Michel, for this very clear talk. I have just a comment about your extreme sensitivity to parameters that you observe. Isn't it just an effect of the fact that your model has very few degrees of freedom, and like in a real GCM, there are many degrees of freedom, and somehow the model is more robust because there are more degrees of freedom?
I think I don't know. It's always tempting, obviously, to say that the more parameters you have, the more messy it should be. I mean, that's the usual argument we use. I mean, Lorentz's system is chaotic, so a GCM must be chaotic. I mean, we have this kind of extrapolation. Here, I just want to add one line of caution about what I call extreme sensitivity to noise. It's the extreme sensitivity of the trajectories. But if you consider, for example, if you want to characterize the attractor, for example, the amplitude of the ice age, or maybe its average frequency, that is a very robust feature of the model. So what it shows is that we have something which is not chaos, but has some flavor of it. And a priori, I don't see why we would not have the same thing if we try to run ice ages with a big model. So I'm tempted to do this extrapolation exactly the same way that you extrapolate from Lorentz's chaos to GCM chaos. This said, and I didn't say this, you also have models of ice ages which are more dynamical system-like than Didier Payar's, which are nonlinear continuous dynamical system equation, which don't display this property of super sensitivity to noise. So in that sense, it's very hypothetical. It's not something that we can consider as a generality of all ice ages model. But that's something I discovered only 2 years ago.
Thank you.
Yes, sir. Thank you. So you mentioned René Thom. He wrote a book with the title "Prédire n'est pas expliquer." So predicting doesn't mean explaining. René Thom.
Sorry, I didn't understand what you said.
René Thom. He wrote a book,
Mm-hmm.
and the title is "Prédire n'est pas expliquer." So predicting doesn't mean explaining. And so, in the context of what you said here, so I mean, it predicts, but what does it explain about the ice ages?
So it does not. So all this stuff explains nothing about the mechanism of ice ages. It just says what you should. It's a good question. It gives you an insight about. What you should expect, what sort of predictability you should expect from a model that has a couple of basic features. If you have a model which is an oscillator, if you have a model that at some point has an acceleration that generates the deglaciation, then there is a good chance that it will have at some point extra sensitivity to the exact values of the parameters or to noise. I think this is what, if we have a prediction, it is that one. So that's the reason why I call it a game around ice ages. We are not proving that the mechanism of deglaciation is related to ice or to CO2 or whatever. And we are at a larger level of abstraction in a certain sense. But we try to take this advantage of this larger level of abstraction to derive general properties of the predictability or the stability of the sequence of ice age. I agree with you, and this is one of these, you know, when you are 42, you start to have this big crisis about the meaning of your life. It's not something we will easily prove, and that explains for him also doing other stuff. But that's the point, yeah.
I like your comment. Yeah, other comments or questions? Yes, please. Yeah, just give me the...
So I'm a little curious about how the trajectory, the fact that it is sensitive to noise and parameters but not to initial conditions. Yeah. Because in the people who do data assimilation, like I come from more of a physical climate model world, people who do data assimilation believe we can use Kalman filter techniques also to do parameter estimation and uncertainty quantification as much as initial conditions. How does it know the difference between the two?
Well, there is an easy way to see it. Well, I hope it's easy. So the mean Lyapunov exponent is lesser than 0. So on average, if you like, the particles are funneled. This is the right English word. I mean, they are brought together most of the time. And while in chaos, I would say most of the time they are being dispersed. And sometimes you have convergence and divergence, but most of the time it's dispersed. So here it's most of the time converging, and then you have a few critical times where the particles are being split. So that's the key idea, is that the stringent chaotic attractor, I don't have this figure here, maybe I should have shown it, but if you visualize a distance between the attractor and the repeller, it almost touches, but at a number of finite times. So basically it means that you have a few crucial and quite well located dangerous times. I would, if you like a kind of word, it's a kind of time of indecision. So it means that most of the time, the Kalman filter will work.
Other comments or questions? If not, I think we're done. Thanks a lot, Michel.
Thank you.